A capacitor is an electronic component that can store electric charge and release it when needed, similar to a small, rechargeable battery. High voltage. How it works. The image shows two comparisons. Left side, battery. A battery stores energy using chemical reactions. Right side, capacitor. A capacitor stores energy in an electric field formed between two metal plates separated by an insulator, dielectric, shown as the blue area. Battery. Key difference. A battery stores energy chemically and releases it slowly. A capacitor stores energy electrically and can release it very quickly when needed. In short, greater than a capacitor is like a temporary battery. It charges, holds energy, and discharges, but works through electric fields, not chemicals. A basic capacitor has three main parts. 1. Two metal plates, conductors. These plates store electric charge. One becomes positively charged, and the other negatively charged. 2. An insulating layer between them, called the dielectric. The dielectric separates the two plates so that current cannot flow directly between them. Instead, it allows an electric field to form, which stores energy. Puzzle piece. Dielectric material. The dielectric can be made of different insulating materials such as air, plastic, ceramic, paper, mica. Each material affects how much charge the capacitor can store. This property is called the dielectric constant. Framed picture in the image. The two gray plates represent the metal conductors. The yellow area in between is the dielectric, insulating layer. In short, a capacitor is made of two metal plates separated by an insulator, dielectric, that helps store electric energy safely and efficiently. High voltage. Main concept. Capacitance, C, tells us how much charge, Q, a capacitor can store for a given voltage, V. Mathematically, greater than C equals epsilon times A, D, where C equals capacitance epsilon, epsilon equals dielectric constant. How good the insulating material is. A equals area of the plates, D equals distance between the plates. Triangle ruler factors affecting capacitance. 1. Area of plates, A, larger plate area, right pointing arrow, more space to store charge. Up triangle, larger A equals higher capacitance. 2. Distance between plates, D, smaller distance, right pointing arrow, stronger electric field. Down triangle, smaller D equals higher capacitance. 3. Dielectric material, epsilon, better insulating material, right pointing arrow, more charge can be stored for the same voltage. Puzzle piece. Higher epsilon equals higher capacitance. Framed picture in the image. The gray plates are the conductors. The blue area represents the dielectric, insulator, between them. The formula at the bottom shows the mathematical relationship between capacitance, plate area, distance, and dielectric. In short, a capacitor's ability to store charge increases with larger plates, closer spacing, and a better dielectric material. High voltage charging. When a capacitor is connected to a power source, like a battery, it begins to store electrical charge. One plate becomes positively charged, plus, and the other becomes negatively charged, minus. The insulating layer, shown in yellow in the image, between the plates prevents current from flowing directly, so energy is stored as an electric field. Battery discharging. When the capacitor is disconnected from the power source and connected to a circuit, it releases the stored energy. The stored charge flows out, providing power to the connected load, like a bulb or motor, for a short time. Camera with flash example. In a camera flash, capacitors store energy from the battery and then discharge it quickly to produce a bright flash of light. This shows how capacitors can deliver energy instantly when needed. In short, a capacitor works like a temporary battery. It stores energy when charging and releases it when discharging. High voltage. What is capacitance? Capacitance measures how much charge a capacitor can store for a given voltage. It depends on the structure and materials used in the capacitor. Clipboard factors affecting capacitance. 1. Area of plates, A. The larger the surface area of the plates, the greater the capacitance. Bigger plates can hold more charge. 2. Distance, D, between plates. The smaller the distance between the plates, the higher the capacitance. Shorter separation means a stronger electric field and more stored charge. 3. Dielectric material. The yellow layer between plates represents the dielectric, an insulating material. A better dielectric, higher epsilon, increases the capacitance because it allows more charge to be stored without leakage. Book formula: C equals epsilon times left frac A D right, where C equals capacitance epsilon equals dielectric constant, depends on material, A equals area of plates, D equals distance between plates. In summary, a capacitor's ability to store charge increases with larger plate area, smaller gap, and better dielectric material. Keycap 1 ceramic capacitor. Appearance: small, disc-shaped, usually orange or brown. Features: small capacitance, very stable, and non-polarized. Use: ideal for high-frequency circuits, signal filtering, and decoupling because they respond quickly. Keycap 2 electrolytic capacitor. Appearance: cylindrical shape with polarity markings, plus and. Features: large capacitance but polarized, must connect the right way. Use: commonly used in power supplies for smoothing voltage and energy storage. Keycap 3 tantalum capacitor. Appearance: small rectangular body, usually yellow or orange, with a plus marking. Features: very stable, reliable, and compact. Has better performance than electrolytic capacitors in some cases. Use: found in precision circuits like smartphones and medical devices. Keycap 4 film capacitor. Appearance: box-shaped, often blue. Features: non-polarized, stable over temperature, and durable. Use: used in AC circuits, filtering, and audio crossover networks. Keycap 5 supercapacitor, ultracapacitor. Appearance: large cylindrical shape, similar to electrolytic capacitors. Features: can store huge amounts of energy compared to other capacitors. Use: used in energy storage, backup power, and electric vehicles for quick charge and discharge cycles.